Section 1 Introduction. We're here to introduce our work on a new architecture for large language models, which we call retentive networks or RetNet. The transformer model has been the go-to choice for these types of models, primarily because it solved the problem of sequential training that was inherent in recurrent models. However, the transformer model isn't perfect. It allows for parallel training, but this comes at the expense of efficient inference. This is due to the model's complexity per step and its memory-bound key-value cache, which makes it difficult to deploy. As the sequence length grows, so does the GPU memory consumption, latency, and the inference speed decreases. Many researchers have tried to develop a new architecture that retains the benefits of the transformer model, such as training parallelism and competitive performance, while also offering efficient inference. However, achieving all these goals at once has proven to be a challenge, often referred to as the impossible triangle. There have been three main approaches to this problem. The first is linearized attention, which approximates standard attention scores with kernels, allowing for inference to be rewritten in a recurrent form. However, this method falls short in terms of modeling capability and performance compared to the transformer model. The second approach goes back to recurrent models for efficient inference, but this sacrifices training parallelism. To counter this, element-wise operators are used for acceleration, but this harms representation capacity and performance. The third approach explores replacing attention with other mechanisms. However, none of these methods have been able to overcome the impossible triangle, and none have clearly outperformed the transformer model. Our proposed solution, RetNet, aims to solve these issues. It offers low-cost inference, efficient long-sequence modeling, performance comparable to the transformer model, and parallel model training. We achieve this by introducing a multi-scale retention mechanism to replace multi-head attention. This mechanism has three computation paradigms: parallel, recurrent, and chunkwise recurrent representations. The parallel representation allows for full utilization of GPU devices during training. The recurrent representation enables efficient inference in terms of memory and computation, significantly reducing deployment cost and latency. The chunkwise recurrent representation allows for efficient long-sequence modeling. We encode each local block in parallel for computation speed, while encoding the global blocks recurrently to save GPU memory. We've conducted extensive experiments comparing RetNet with the transformer model and its variants. The results show that RetNet consistently performs well in terms of both scaling curves and in context learning. Furthermore, the inference cost of RetNet doesn't change with sequence length. For a model with 7 billion parameters and a sequence length of 8,000, RetNet decodes over 8 times faster and uses 70% less memory than transformers with key-value caches. During training, RetNet also saves 25 to 50% memory and accelerates the process by 7 times compared to the standard transformer model. Moreover, RetNet's inference latency isn't affected by batch size, allowing for high throughput. These promising properties make RetNet a strong contender to succeed the transformer model for large language models. Section Summary. The transformer architecture has become popular for large language models, but it suffers from inefficient inference due to high computational complexity and memory usage. Previous research has attempted to address this issue by approximating attention or using recurrent models, but none have been able to achieve both efficient inference and competitive performance. In this work, we propose RetNet, a new architecture that combines parallel, recurrent, and chunkwise recurrent representations to achieve low-cost inference, efficient long-sequence modeling, and transformer-comparable performance. Experimental results show that RetNet outperforms transformers in terms of decoding speed and memory usage, making it a strong contender for large language models. Section 2 Retentive Networks. We're going to discuss a concept called retentive networks, or RetNet for short. This network is made up of several identical blocks, L to be exact, and it's structured similarly to a transformer, with residual connections and pre-layer norm. Each block in the RetNet consists of two parts: a multi-scale retention (MSR) module and a feed-forward network (FFN) module. We'll focus on the MSR module for now. Let's say we have an input sequence, which we'll call X, made up of individual elements X1, X2, and so on, up to the length of the sequence. The RetNet processes this sequence in an autoregressive manner. The input vectors are first grouped into a matrix X0, which is in the shape of the sequence length by the hidden dimension size. Then, we calculate contextualized vector representations for each layer of the RetNet. Now, let's talk about the retention mechanism, which has a dual form of recurrence and parallelism. This allows us to train the models in parallel while also conducting inference in a recurrent manner. We start with the input matrix X and project it to a one-dimensional function versus n, by multiplying each element of X with a weight vector WV. We can think of this as a sequence modeling problem where we want to map versus n to O, n, through a series of states, which we'll denote as S_n. We can simplify this mapping process by using a recurrent formula where each state S_n is a combination of the previous state S_n1 and the current input versus _n, multiplied by a transpose of a matrix K_n. Next, we map versus _n to the state vector S_n and then apply a linear transformation to encode sequence information in a recurrent manner. We make the projection matrices Q and K content aware by multiplying X with learnable matrices WQ and weak respectively. We then diagonalize a matrix A and obtain a new form of A that can be raised to the power of nm. By absorbing a matrix lambda into WQ and weak, we can rewrite the equation to show how O_n is calculated as a sum of terms, each of which is a product of Q_n, K_m, and V_m, all modified by a factor related to their relative positions. We further simplify this by considering gamma as a scalar, leading to a new equation for O_n. This equation is easily parallelizable within training instances. In summary, we start with a recurrent modeling approach and then derive a parallel formulation. We consider the original mapping from V, n, to O, n, as vectors and obtain the retention mechanism. Section summary. The retentive network, RetNet, consists of stacked blocks, each containing a multi-scale retention, MSR, module and a feed-forward network, FFN, module. The MSR module encodes the input sequence in an autoregressive manner, while the retention mechanism combines recurrence and parallelism to train the models in a parallel way. By formulating the mapping from input to output in a recurrent manner and then deriving its parallel formulation, the retention mechanism enables efficient and effective sequence modeling. Section. The parallel representation of retention. We're going to discuss two different ways of representing retention: the parallel representation and the recurrent representation. In the parallel representation, we define a retention layer using three elements: Q, K, and V. Q is the product of our input X and a weight matrix W_Q, all multiplied element-wise by a complex number theta. K is similar, but it's multiplied by the complex conjugate of theta. V is simply the product of X and another weight matrix W_V. Theta is a complex number that's calculated using the formula in theta, where I is the imaginary unit and n theta is a variable. We also define a matrix D, which combines causal masking and exponential decay along relative distance. If n is greater than or equal to m, D is equal to gamma nm, where gamma is a constant. If n is less than m, D is 0. The retention of X is then calculated by multiplying Q and the transpose of K element-wise by D, and then multiplying the result by V. This parallel representation allows us to train our models efficiently using GPUs. The recurrent representation of retention is a bit different. It's written as a recurrent neural network, RNN, which is beneficial for inference. For each time step n, we calculate an output S_n by multiplying the previous output S_n1 by gamma and adding the product of the transpose of K_n and V_n. The retention of X_n is then calculated by multiplying Q_n and S_n. We can also use a hybrid form of these two representations to speed up training, especially for long sequences. We divide the input sequences into chunks and use the parallel representation to calculate within each chunk. For information that crosses chunks, we use the recurrent representation. To calculate the retention output of the ith chunk, we first define Q_i, K_i, and V_i as the corresponding elements of Q, K, and V for that chunk. We then calculate R_i as the sum of the product of the transpose of K_i and V_i and gamma_b times the previous R value. The retention of X_i is then calculated as the sum of two terms: the product of Q_i, the transpose of K_i and V_i, which we call the inner chunk, and the product of Q_i and R_i, which we call the cross chunk. The cross chunk term is also multiplied by a factor xi, which is equal to gamma_i plus 1. In this context, I refers to the ith chunk, so X_i is the sequence of X values from I1, B plus 1 to IB. Section summary. The retention layer in the proposed mechanism is defined using parallel representation, which allows efficient training of models with GPUs. Additionally, the mechanism can also be expressed as recurrent neural networks, RNNs, which is beneficial for inference. To accelerate training for long sequences, a hybrid approach combining parallel representation within each chunk and recurrent representation for cross-chunk information is used. Section 2.2 Gated Multiscale Retention. In this section, we discuss the concept of gated multiscale retention. We use a certain number of retention heads in each layer, which is calculated by dividing the model's dimension by the head's dimension. Each head uses different parameter matrices, and multiscale retention assigns a unique gamma value to each head. To keep things simple, we set the gamma value to be the same across different layers and keep them constant. We also introduce a gate to enhance the non-linearity of the retention layers. To explain this formally, let's consider an input x. We define the layer as follows. The gamma value is calculated as 1 minus 2 to the power of negative 5 minus the range from 0 to the number of heads. This is represented as a vector in real numbers. The output of each head is calculated by applying the retention function to the input x and the corresponding gamma value. The output y is then obtained by normalizing the concatenated outputs of all heads. The multiscale retention of x is then calculated by applying a gate to the product of x and a learnable parameter matrix, and then multiplying the result by the output y and another learnable parameter matrix. The normalization process ensures that the output of each head is standardized, following a method proposed in previous research. It's important to note that each head uses multiple gamma scales, resulting in different variance statistics. Therefore, we normalize the outputs of each head separately. We also discuss the normalization of the retention score. We take advantage of the scale invariant nature of the normalization process to improve the numerical precision of the retention layers. Specifically, multiplying a scalar value within the normalization process does not affect the outputs and backward gradients. We implement 3 normalization factors. First, we normalize the product of Q and the transpose of K by dividing it by the square root of the head's dimension. Second, we replace D with a new value calculated by dividing D by the square root of the sum of all D values. Third, we let R denote the retention scores, which is the product of Q and the transpose of K and D. We normalize R by dividing it by the maximum of the sum of all R values and 1. The output of the retention function is then calculated as the product of the normalized R and V. These techniques do not affect the final results but stabilize the numerical flow of both forward and backward passes due to the scale invariant property. Section Summary. In this section, the authors introduce a gated multiscale retention mechanism for each layer of the model. They use multiple retention heads with different parameter matrices and assign different gamma values to each head. They also add a gate to increase non-linearity. The authors normalize the output of each head separately due to the use of multiple gamma scales, and they utilize the scale invariant nature of group norm to improve numerical precision by implementing 3 normalization factors. Section 2.3 Overall Architecture of Retention Networks. We're going to discuss the overall structure of retention networks in this section. Imagine a retention network with L layers. We construct this model by stacking multi-scale retention, MSR, and a feed-forward network, FFN. To start, we take an input sequence and convert it into vectors using a word embedding layer. We then use these embedded vectors as the input for our model. Now, let's talk about how we calculate the output of the model. We use a process that involves the MSR and the FFN. First, we apply a layer normalization to the input, then pass it through the MSR. We add the result to the original input. This gives us an intermediate output. Next, we take this intermediate output, apply layer normalization again, and pass it through the FFN. We add the result to the intermediate output to get the next input. We repeat this process for each layer in the network. The FFN part of the process involves applying a function called JLU to the input multiplied by a parameter matrix, and then multiplying the result by another parameter matrix. When it comes to training the model, we use parallel and chunkwise recurrent representations. This approach allows us to efficiently use GPUs to speed up computation. It's particularly useful for training with long sequences, as it's efficient in terms of both computational operations and memory usage. During inference, we use a recurrent representation that works well with autoregressive decoding. This approach reduces memory usage and inference latency while still achieving equivalent results. Now, let's compare retention networks with previous methods. Retention networks have a linear memory complexity for long sequences, thanks to the chunkwise recurrent representation. When compared to transformers, the parallel representation of retention has similar principles. The Lex transformer, which uses XPOS as position embeddings, is the most similar variant. Retention aligns with XPOS, as described in the equation. However, Retention removes the softmax function and enables a recurrent formulation, which greatly benefits inference. Section summary. The overall architecture of retention networks involves stacking multi-scale retention, MSR, and feed-forward network, FFN, layers. The training process utilizes parallel and chunkwise recurrent representations, while the inference phase employs the recurrent representation for autoregressive decoding. RetNet differs from previous methods by achieving linear memory complexity for long sequences and removing softmax in favor of a recurrent formulation, which improves inference efficiency. Section S4. We're going to simplify and paraphrase the given section of the paper. In section S4, we discuss a situation where if Q_n and K_n are not aware of the content, the formulation can be simplified to S4. Here, O is the result of a series of operations involving Q, K, A, and V. We then move on to linear attention. Typically, different kernels are used to replace the softmax function. However, linear attention has a limitation. It struggles to encode position information effectively, which can make the models less effective. Instead of trying to approximate the softmax function, we decided to reevaluate sequence modeling from the beginning. We then discuss the attention-free transformer, AFT, and RWKV. AFT simplifies dot product attention to element-wise operations and moves the softmax function to key vectors. RWKV, on the other hand, replaces AFT's position embeddings with exponential decay and runs the models recurrently for training and inference. Retention, in comparison, preserves high-dimensional states to encode sequence information, which contributes to expressive ability and better performance. We also mention XPOS and ROPE, which are similar to the relative position embedding methods proposed for transformers. In the retention layer, we use sublayer norm to normalize outputs. Because the multi-scale modeling leads to different variances for the heads, we replace the original layer norm with group norm. In the experiment section, we evaluate RetNet through language modeling and various benchmarks, including language modeling performance, and zero-few-shot learning on downstream tasks. We also compare speed, memory consumption, and latency for training and inference. In the setup section, we discuss parameter allocation. We simplify the parameters in MSR and FFN for fair comparisons. In transformers, there are about 4D-2 parameters in self-attention and 8D-2 parameters in FFN. In comparison, RetNet has 8D-2 parameters in retention. The head dimension of V is twice Q, K. The widened dimension is projected back to D by W_O. To keep the parameter number the same as transformer, the FFN intermediate dimension in RetNet is 2D. We set the head dimension to 256 in our experiments, i.e., 256 for queries and keys, and 512 for values. For fair comparison, we keep gamma identical among different model sizes. Section summary. The section discusses different attention mechanisms and their limitations. It introduces the attention-free transformer, AFT, and retention models as alternatives to the traditional dot product attention mechanism. The RetNet model is evaluated through experiments on language modeling, zero-few-shot learning, and comparisons of speed, memory consumption, and latency. The parameter allocation in RetNet is adjusted to maintain the same number of parameters as the transformer model. Section. Language model training. We've trained various language models of different sizes, specifically 1.3 billion, 2.7 billion, and 6.7 billion parameters, from the ground up. The training data we used is a carefully selected mix of the pile, C4, and the stack. To signal the start of a sequence, we add a beginning of sequence token, which we found to be beneficial for the stability and effectiveness of the training process. Our training batch size is 4 million tokens, with a maximum length of 2048. We train the models using 100 billion tokens, which equates to 25,000 steps. For optimization, we use the Atom W optimizer with a first beta value of 0.9 and a second beta value of 0.98, and we set the weight decay to 0.05. We use 375 warm-up steps and a linear learning rate decay. To ensure stable training, we initialize the parameters following the DeepNet method. Our implementation is based on torch scale, and we use 512 AMD MI200 GPS for training. We've evaluated our language model's perplexity on a validation set, using both transformer and RetNet architectures. We've tested 3 model sizes, and found that RetNet performs comparably to transformers. Interestingly, RetNet seems to be more favorable when it comes to scaling up the model size. In addition to its performance, RetNet's training process has proven to be quite stable in our tests. Our experimental results suggest that RetNet is a strong contender against Transformer for large language models, especially when the model size exceeds 2 billion parameters. We've also tested our language models on a variety of downstream tasks. We've evaluated both zero-shot and four-shot learning using the 6.7 billion parameter models. The datasets we used include Hella Swag, BoolQ, Copa, PIQA, Winograd, Winagrande, and StoryClose. The accuracy results are consistent with the perplexity results we obtained from language modeling. RetNet performs comparably to Transformer in both zero-shot and in-context learning settings. Section summary. The authors trained language models of different sizes, 1.3b, 2.7b, and 6.7b, using a curated compilation of the PILE, C4, and the STAT datasets. They found that appending the less than boss greater than token at the beginning of the sequence improved training stability and performance. The models were trained using the Atom W optimizer with specific parameters and were initialized following DeepNet for stability. They compared the performance of RetNet and Transformer models, finding that RetNet outperformed Transformer for model sizes larger than 2b. Additionally, they evaluated the models on various downstream tasks, where RetNet achieved comparable performance to Transformer. Section 3.3 Training Cost. In this section, we'll discuss the training and inference costs of our model, RetNet, in comparison to other models like Transformer and Flash Attention. We'll look at factors like training speed, memory usage, and the length of the training sequence. We conducted our tests using a sequence length of 8,192 and compared the results of RetNet and Transformer. We also included Flash Attention in our comparison, a model known for its speed and efficient GPU memory usage due to its use of recomputation and kernel fusion. For our RetNet model, we used basic PyTorch code and didn't incorporate any acceleration techniques like kernel fusion or Flash Attention. However, we plan to explore these in the future. Our RetNet model uses a chunkwise recurrent representation of retention, as described in a previous equation. We set the chunk size to 512 for these tests. We used 8 NVIDIA A100-80GB GPUs for our evaluations because Flash Attention performs exceptionally well on this type of GPU. We also enabled tensor parallelism for our larger models, those with 6.7 billion and 13 billion parameters. Our results showed that RetNet is more memory efficient and has a higher throughput than Transformers during training. Even when compared to Flash Attention, RetNet held its own in terms of speed and memory usage. Plus, RetNet doesn't rely on specific kernels, making it easy to train on various platforms. For instance, we successfully trained RetNet models on an AMD MI200 cluster with good throughput. We also believe that RetNet has the potential to further reduce costs with advanced implementation techniques like kernel fusion. Next, we compared the memory cost, throughput, and latency of Transformer and RetNet during inference. Transformers reuse KV caches of previously decoded tokens, while RetNet uses the recurrent representation as described earlier. We tested the 6.7 billion parameter model on the A100-80GB GPU. Our results showed that RetNet outperforms Transformer in terms of inference cost. The memory cost of Transformer increases linearly due to KV caches, while RetNet's memory usage remains consistent, even with long sequences. This means RetNet requires much less GPU memory. In fact, the additional memory consumption of RetNet is almost negligible, about 3%, while the model weights occupy the remaining 97%. Section summary. The training cost comparison between Transformer, RetNet, and Flash Attention shows that RetNet is more memory efficient and has higher throughput than Transformers during training. RetNet is also competitive in terms of speed and memory cost compared to Flash Attention, and it can be easily trained on other platforms efficiently. In terms of inference cost, RetNet outperforms Transformer by requiring much less GPU memory and maintaining consistent memory consumption even for long sequences. Section Throughput. We'll now discuss the throughput, latency, and comparison with Transformer variants of our model, RetNet. Starting with throughput, we've observed that as the decoding length increases, the throughput of the Transformer model decreases. However, RetNet maintains a consistent throughput regardless of the decoding length, thanks to its use of recurrent representation of retention. Next, let's talk about latency, which is a crucial factor in deployment as it significantly impacts user experience. Our experiments show that as the batch size increases, the latency of the Transformer model also increases. Furthermore, the latency of Transformers grows more rapidly with longer input. To keep latency at an acceptable level, we need to limit the batch size, which unfortunately reduces the overall inference throughput of Transformers. On the other hand, RetNet's decoding latency is not only lower than transformers but also remains almost constant across different batch sizes and input lengths. We also compared RetNet with several efficient transformer variants, including linear transformer, RWKV, H3, and Hyena. All these models have 200 million parameters with 16 layers and a hidden dimension of 1024. For H3, we set the head dimension as 8. For RWKV, we replaced self-attention layers with the time mix module, while keeping FFN layers consistent with other models for a fair comparison. We trained the models with 10,000 steps with a batch size of 0.5 million tokens. Most hyperparameters and training corpora remained the same as in the previous section. Our results showed that RetNet outperformed previous methods across different datasets. Not only did RetNet achieve better evaluation results on the in-domain corpus, but it also obtained lower perplexity on several out-of-domain datasets. This impressive performance, along with significant cost reduction, makes RetNet a strong successor to Transformer. Lastly, we'll discuss the training and inference efficiency of the compared methods. Let's denote the hidden dimension as D and the sequence length as N. For training, RWKV's token mixing complexity is proportional to the product of D and N, while Hyena's is proportional to D times N times the logarithm of N with fast Fourier transform acceleration. These two methods reduce training flops by using element-wise operators to trade off modeling capacity. In comparison, the chunk-wise recurrent representation in RetNet is proportional to D times N times the sum of the chunk size and the head dimension, which we usually set as 512 and 256 respectively. For either large model size, i.e., larger D, or sequence length, the additional chunk size and head dimension have negligible effects. Therefore, RetNet's training is quite efficient without sacrificing the modeling performance. For inference, among the compared efficient architectures, Hyena has the same complexity per step as Transformer, while the others can perform constant time decoding. Section summary. The throughput of the Transformer model decreases as the decoding length increases, while RetNet maintains a higher and consistent throughput by utilizing recurrent representation. In terms of latency, increasing batch size leads to higher latency for transformers, and their latency also grows faster with longer input. On the other hand, RetNet outperforms transformers in terms of decoding latency, maintaining similar latency across different batch sizes and input lengths. RetNet also outperforms various efficient transformer variants in terms of evaluation results on different datasets, making it a strong successor to Transformer. The training and inference efficiency of RetNet is also favorable, with efficient training and comparable inference complexity to other efficient architectures. Section 3.6 Ablation Studies. In Section 3.6, we conduct ablation studies to evaluate the impact of different design elements of RetNet on language modeling. The evaluation criteria and metrics remain consistent with those used in previous sections. We first examine the role of the gate and group norm, as detailed in earlier sections. Our findings suggest that these two components significantly enhance the final performance of the model. The gating module, in particular, is crucial for increasing nonlinearity and boosting the model's capabilities. It's important to note that we maintain the same parameter allocation as transformers, even after removing the gate. Additionally, the use of group normalization in retention helps balance the variances of multi-head outputs, leading to improved training stability and better language modeling results. Next, we explore the use of different decay rates, represented by the symbol gamma, for the retention heads. In these studies, we consider two scenarios, one where we remove gamma decay, referred to as gamma decay, and another where we apply the same decay rate across all heads, referred to as multi-scale decay. In the first scenario, removing gamma decay is the same as setting gamma equal to 1. In the second scenario, we set gamma equal to 127 divided by 128 for all heads. Our findings suggest that both the decay mechanism and the use of multiple decay rates contribute to improved language modeling performance. Lastly, we look at the impact of head dimension on the model's performance. From a recurrent perspective, the head dimension represents the memory capacity of hidden states. In this study, we decrease the default head dimension from 256 to 64, meaning we use 64 for queries and keys, and 128 for values. We keep the hidden dimension, represented by the symbol D with subscript, model, the same, which results in an increase in the number of heads. Our experiments show that a larger head dimension leads to better performance. Section summary. In this section, the authors conduct ablation studies on various design choices of RetNet and evaluate their impact on language modeling results. They find that the gating module and group norm significantly improve the model's performance by enhancing non-linearity and balancing variances. Additionally, they explore different decay rates and head dimensions, concluding that both the decay mechanism and larger head dimensions contribute to better language modeling performance.